2025 A-Level Combined Mathematics Paper 2 Part A question number 7. This question has to do with equilibrium of forces. The question says, a uniform rod AB of weight W making an angle alpha which is somewhere in between 0 and pi by 2 radians with the downward vertical is kept in equilibrium by placing the end B touching a smooth vertical wall while the other end A is suspended by a light inextensible string attached to the wall at a point C which is vertically above the point B as shown in the figure. The string is taut and makes an angle theta with the downward vertical. The rod and the string are lying in a vertical plane perpendicular to the wall. Given this information, we are asked to show that tan alpha is equal to tan theta. So we are asked to show a very simple thing, but we have a lot of setup for it. If we take a look at the diagram, we can see they have drawn out the rod AB here. They've also drawn out the line AC, which is representative of the inextensible string that we have. Considering the diagram, we can see there are some forces that are missing. On the wall, there should be a normal reaction here of R. Now, since the wall is smooth, there's not going to be any friction, so we're only going to have this normal reaction, which is going to be acting in the horizontal direction. Considering the string, we're also missing a tension force here of T, which I'm going to mark. Additionally, we have to note that since the rod is uniform, this weight W acting on the rod is acting at the midpoint of the rod. If we call that midpoint, say D, then AD is going to be equal to DB. Now I'm going to mark all of these in a separate diagram, not this diagram here, because I additionally also want to mark a couple extra things. So if I draw this diagram, we can see we have a vertical downward like this. We have the rod, we'll draw the rod down here, and then this other line above the rod is going to be the string. So we have the point C up here, with the point A here, with the point B here. This angle here based on the diagram is going to be alpha. This angle is going to be theta. There's going to be a tension here. There's going to be a weight W down here. And I'm going to call the midpoint at which the weight is acting the point D. Additionally, on the wall at the point B, there's going to be a normal reaction which I'm going to call R. So now these are all the forces marked. Additionally, I'm going to let the length AB be equal to L. The reason I'm doing this is because it's going to be handy later. But for now, we'll just let it be L and leave it like that. So now given this, how would we analyze this situation and construct equations that we can use to show that tan alpha is equal to 2 tan theta? Well, one of the things that you might immediately notice is that on the rod AB, there are only three forces. There's the force R, the force T, and the force W. Now, given three forces, we know that these three forces must obey the triangle law, meaning that if you connect all three of them together, since the rod is in equilibrium, all three of the forces must make a full complete triangle. So given this, we could try to construct a triangle with these three, and doing so, we could get some equation that we can use in order to find tan alpha equals 2 tan theta. But there is another more basic way that we could find the same exact equations using these three forces, and that is to simply resolve them into two directions and then consider equations using F equals ma. Now in this case, for this question, I'm actually going to use that more simple method, and the reason for that is that the triangle law method is far easier than this method. So if I can do this method and therefore you can do this method, you can also easily do the triangle method. So considering resolving, what we have to do is apply F equals ma to the system. So we're going to apply F equals ma, we're going to apply it in two directions, the horizontal direction like this and the vertical direction like this. Now considering both of these directions, since the rod is in equilibrium, the forces overall in each of these directions are going to be 0, and therefore the acceleration A in both of these directions horizontally and vertically is going to be 0, and therefore ma is also going to be 0 in both of these directions. So therefore the product ma for both of these is going to be 0, so I can write immediately on the right hand side both of these equations are going to have 0. Now as for the left hand side, if we consider the situation, in the horizontal direction, we have a force R, but that R is acting in the left direction. Since I drew the arrow in the right direction, R is going to be a negative number. So therefore, we have negative R. Now this is going to be added to the extra forces that we have in the horizontal direction, which if we look, W is vertical, so it doesn't come, but T has a horizontal component and a vertical component, and the vertical component is going to be ignored, but the horizontal component here is going to be taken. So if we consider the horizontal component, we can see since this angle here is theta, this side is going to be sine theta, and therefore the horizontal component of T is going to be T sine theta. So we have negative R plus T sine theta. Now similarly, considering the vertical upward direction, since W is downward, we're going to have negative W, and then additional to this we're going to have the vertical component of t, which if you look from this triangle you can see is going to be the cosine value of theta. So therefore the vertical component of t is going to be t cosine theta. We're going to call this equation number 1 and equation number 2. Now considering equation number 1 and 2, if we take 1 comma 2, we can see from 1 we can rearrange this to t sine theta is equal to r, and from 2 we can rearrange this to t cos theta equals w. Now if we divide 1 by 2, we can see on one side we're going to have t sine theta divided by t cos theta. The t's are going to cancel, leaving us with just sine theta divided by cos theta, which is going to be tan theta. So on one side we're going to have tan theta. On the other side, if we consider dividing this by this, we're going to have r divided by w. So therefore tan theta is equal to r divided by w. We're going to call this equation number 3. Now we already have tan theta, which is one of the things that we need in order to find this equation. What we need to do now is to find equations in terms of tan alpha and use that in order to establish the relationship between tan alpha and tan theta. Now to do that, what we're going to do is to consider moments about the point A. Because if you consider the point A here, we can see the force T passes through the point A, and therefore if you consider moments, T is going to have 0 moments about A. But if you consider the other two forces, R is going to have a moment and W is going to have a moment about A. So therefore we're going to have a relationship between R and W, which can eventually get us R divided by W, which means that this equation can be relevant to the equation that we form from the moments around A. Now furthermore we can see we're also going to have tan or sine or cosine of alpha involved in this, since we can see if we consider the lengths involved, this W is going to have a moment considering this distance right here, and this force R is going to have a moment considering this distance right here. So therefore we are going to have alpha in this no matter what. Now before we start with the moments, we're going to also label this angle here as also being alpha, since it is also alpha. This is vertical downward, this is vertical downward, and this line is a single straight line. So therefore if this angle is alpha, this angle is also alpha. Now considering the length AB, if AB is equal to L, since AB is going to be divided into two pieces by the point D, AD is going to be equal to DB is going to be equal to L. Now considering that, if we consider the moments around A like this, for the weight W downward like this, we can see the distance perpendicular is going to be this distance right here. If this distance here is, actually I made a mistake, it's L divided by 2, not L. So anyway, L divided by 2. So if this distance is L divided by 2, this distance based on this angle is going to be L divided by 2 sine alpha. So therefore the moment contributed by W is going to be L divided by 2 sine alpha times W. But we can see if we take the moments in the anti-clockwise direction, since W is providing moment in the clockwise direction, we're going to have negative W L divided by 2 sine alpha. Now in addition to this, if we consider R is going to be providing a moment in anti-clockwise direction, so it's going to be positive, so we're going to have positive R times the length, which if you consider the length involved, this entire length AB is going to be equal to L, and considering the triangle that we want, this length here is going to be L cosine alpha. So therefore we have L cosine alpha, which I'm actually going to erase this multiplication sign and just write directly R times L cosine alpha. And the total moments here, since we're at equilibrium, is also going to be equal to 0. Now from this, if we consider what we have, we can divide all of the L's in this equation here, leaving us with minus W over 2 sine alpha is equal to R cos alpha. Now if we plus R cos alpha is equal to 0, which we can lead to W over 2 sine alpha equals R cos alpha, which is what I actually wanted to find, which is equation number 4. Now from equation number 4 we can see, actually I'll actually rearrange this one more time. We can see if we divide both sides by cos alpha and divide both sides by W over 2, we can get sine alpha divided by cos alpha, which is tan alpha, which is equal to R divided by W over 2, which is going to be 2R over W, which I'm now going to call equation number 4. Previously I could have used that equation number 4 that I defined earlier, but this equation number 4 is easy to work with. It's easy to work with because if you consider what we have here, we have 2 times R divided by W, and R divided by W was found to be equal to tan theta, meaning that we can directly substitute into here that tan alpha is equal to 2 times tan theta, which is exactly what we wanted in the question right here. So if we do that, if we do 3, 4, we can see that this will lead us to tan alpha equals 2 times r divided by w, which is tan theta, so 2 tan theta, which is exactly what we wanted in the question, and therefore this is going to be the end of our solution for this question. Now finally, if you consider the marks given for this question, if you do the triangle method, you're going to get 10 marks directly for drawing the triangle, but if you do it by this method, you're going to get 5 marks for this part for resolving the horizontal direction, and you're going to get 5 marks for resolving the vertical direction. Now furthermore, when you combine the two to get tan theta is equal to r divided by w, you're going to get another 5 marks. After this, when you consider the moments around A, you consider them and you get this equation right here, which eventually leads you to tan alpha equals 2 times r divided by w. You get another 5 marks, and when you combine the two to finally get tan alpha is equal to 2 tan theta, you get another 5 marks. And that is going to be all for this question and all for this video. So I hope you enjoyed. If you have any feedback, post them in the comments down below. Thank you for watching, and goodbye.